Hello, wonderful people. As we all get very excited by the latest sets of cosmology results indicating the possibility of new fundamental physics, today's talk might or might not have a lesson we'll look back on in a few years. We have today the KiDS legacy analysis, the final data release and cosmological analysis from the Kilo-Degree Survey, who in 2025 are one of the three major cosmic shear surveys. And, as we will see, with a full understanding of the data, the telescopes involved and the relevant modelling issues, the once tantalising S8 tension seems to have completely evaporated, at least when it comes to the Kilo-Degree Survey. Joining us today are Angus Wright from Ruhr University in Bochum, Benjamin Stölzner, also at Ruhr University in Bochum, Robert Reischke at the University of Bonn, Marika Asgari at Newcastle University, and Konrad Kuijken at the University of Leiden. Welcome, everyone. Do you want to start by telling us briefly about KiDS legacy?
Yeah, thanks very much, Sean. We're discussing the publication of the final cosmological analysis of the Kilo-Degree Survey from the fifth and final data release of KiDS. And as part of this data release and cosmological analysis, we're leveraging improved imaging, better calibration, new analysis methods, new modeling, new samplers, basically updates on all fronts to produce some of the most precise cosmological constraints that KiDS has produced to date.
So what new insights did you obtain when doing the final legacy parts of KiDS?
The analysis that we made of the final data set with KiDS was, as is per standard in the field, was done blinded. And our blinded analysis had three possibilities, where one was fully consistent with previous work from KiDS, one was fully consistent with the CMB analyses from Planck, and one was sort of in the middle ground. And much to the surprise of the KiDS team post-unblinding, KiDS legacy was found to be fully consistent with the CMB. And so that was quite a surprise and is the primary conclusion of KiDS legacy.
Did it always kind of feel like you knew there must be hidden systematics and you just had to find them?
It's a really interesting question. I think that we've always been fairly cautious in our framing of the S8 tension, especially from KiDS, in that we've said that the analyses that we have done are our best effort and most reliable analyses to date, but there are always unknown unknowns. And in this case, a majority of the difference between previous KiDS analyses and the results from legacy have come from methodological updates rather than statistical noise. And one of the really great things about KiDS, in particular KiDS legacy, is that at each analysis, we've been able to verifiably demonstrate that this analysis is more robust than the previous one. And so we've really been making positive strides towards better and better analyses. And somewhat unsurprisingly, in retrospect, we've also been marching slowly towards consistency with the CMB with each subsequent release, which is why the consistency or inconsistency with the CMB has remained fairly static, even though constraining power has gone up with each successive release.
I can't get you to speak for the Dark Energy Survey and other groups, but is it your inkling that if they were to be analysing their data, and I guess their data is coming out sometime soon in the next couple of months, will they be saying the same message? Or do you not want to speak for them and let's just move on with the KiDS talk, not the DES talk?
Obviously, it would be presumptuous of me to speak on behalf of my DES colleagues, but knowing the quality of the analysis that we have put together here, and the consistency that we've demonstrated in these papers, it's my opinion that this is the most reliable analysis of cosmic shear that KiDS has put together to date, and this indicates that under that most reliable analysis, we're consistent with Planck. And it would therefore not be surprising to me if similarly reliable analyses from DES were also consistent with the CMB.
How do you know that this is the correct analysis, the one without the tension and not the one in earlier years that had the tension?
So we have conducted an extensive series of internal consistency tests of the KiDS legacy dataset, and some of which are here summarized in this figure. And every single test has shown that the KiDS legacy dataset is more robust than what we have seen before in the KiDS 1000 analysis, and there's not a single one that really suggests that anything is off. So in that sense, our tests really highlight that the data quality is a lot better in KiDS legacy than in previous analyses.
So if you had shown me a plot exactly like this with the KiDS 1000 analysis method, it would not look so tidy?
Exactly. So I will show this a little bit later. So in KiDS 1000, we had some indication for some tension for some specific setup, and this will be different in KiDS Legacy.
Okay, let's get into the background. I guess it's worth reintroducing KiDS itself a little bit, but also why is or was this S8 tension interesting, and why is it so important to be doing these systematic tests?
As we talked about already a bit, there's always the early versus late universe debate. And what we can see here is on the left side, the CMB as measured by Planck, which measures a larger amplitude in the fluctuations. And on the right side, this is actually from KiDS Legacy, the mass map, which at least used to measure, as we now learned, a lower amplitude of the fluctuations in the universe. And there's also, of course, the H0 tension, which is kind of reversed from the values, but this is not what we're talking about. And the question is basically, where does this come from? And there's, of course, the possibility that we have some additional new physics, right? Is lambda CDM correct? Do we have to modify general relativity, our gravitational theory? Or is there some kind of dark energy background component, or even clustering dark energy, some new physics which was responsible for this? Or alternatively, there could also be some astrophysical effects we don't understand, like baryonic feedback, or other systematic effects which might leak in, like the redshift calibration or the shape calibration, or just in general modeling choices we make, which might lead to these differences.
Yeah, and in general, in cosmic shear, we measure the shape of distant galaxies, which are distorted by the matter between us, the observers, and the source galaxies. And this correlates the shape of nearby galaxies, and this allows us to derive constraints on the matter distribution in the universe. And also of particular advantage for cosmic shear is tomography, which is enabled by distance measurements via redshifts of galaxies. And this allows us also to map the mass distribution as a function of the redshift. And in our KiDS legacy analysis, we have also put a lot of time and work into optimizing our analysis methods in order to reduce systematic uncertainties and making them as robust as possible. And this makes KiDS legacy basically a blueprint for upcoming surveys, such as Euclid and LSST, because given the statistical power of these surveys, they will be pretty much systematics dominated. So we're putting a lot of groundwork for these upcoming surveys.
When will LSST be releasing their first kind of cosmological stuff?
I think the plan is to do the main cosmology analysis on year 2.
2027?
Probably, that's my guess, yeah.
Yes, so you might ask why these results are coming out now, why it's taken so long to get to this point, because KiDS started in 2012 and has been taking data for eight years. It ended taking data in 2019. And the short story is this is really hard. And so when KiDS started, most of the methodology that we're using now didn't exist yet. We didn't even understand many of the problems that we would face. So reglancing is actually quite a young field. It started in 2001. In fact, our paper includes a dedication to Nick Kaiser, who did much of the fundamental work setting the scene for how to do this kind of stuff. And over these 25 years, the field has matured as the data got better, as technology allowed us to take better data with larger surveys. And so everything has grown hand in hand, and we've really solved problems as they came along. As the statistical power increased, we also had to improve our systematic control. And so this slide with far too much information just shows over the course of KiDS where we have included innovations either in the data or in the way we analyze the data, in the way we process it, in the way we calibrate it, in the calibration data we bring to bear, in the theoretical modeling. All these things have really continued to grow and improve until we get to the point where we are today.
Yeah, I mean, you say this table has too much information, but it's rare to see a table that when it first pops up on the screen looks so dense on information that is simultaneously like you want to just sit and look at, and it's very, very interesting. Like there's a lot of story being told here about how, yeah, exactly, the analysis methods have increased, and there's heaps of things I'm already wanting to ask about. So one of the things is from K1000 plus to KiDS Legacy, you've only gone from 1,000 square degrees to 1,350, which says that there's not that much statistical increase. But then I also see your photo Z range has increased from a redshift of 1.2 to 2. So actually your statistical data might have increased substantially.
I was going to say, so one important point is even though the area didn't grow so much, actually the volume of data grew quite a bit because we actually include a whole new pass over the survey area. So in one of the critical bands, the survey is quite a bit deeper, which improves the photometric redshifts and is actually what allows us to go deeper.
Right, so the statistical sense of how many galaxies didn't improve, but the statistical sense of how well do you understand each galaxy maybe improved substantially. Wow, okay.
So let me give you an overview of the changes since 2021, when we did the KiDS 1000 cosmic shear analysis using this plot. So the others will give you the details of what these changes mean in the next few slides. First of all, we have two panels here. The right one is showing S8, that is sigma 8 times omega m over 0.3 to the power of 0.5, while the left one is showing capital sigma 8, which has a similar functional form to S8, but the power for omega m is adjusted such that capital sigma 8 shows the direction of the smallest error or the highest constraints for this combination of parameters. So you can follow either of these two panels. It doesn't matter so much. They're showing basically the same thing. And then also note that the value for the power of omega m here is fixed to 0.58, which is the best choice for our fiducial legacy analysis. So it might not be the best choice for all the points that you're going to see here. And the red point is showing the Planck legacy fiducial results, result which includes both primary and secondary anisotropy, so includes the CMB lensing as well. And this is in contrast to what we had in Asgari et al. 2021. We were just looking at the primary one, so without CMB lensing. That's why the numbers you see on the right-hand side are a little bit different to what we had in that paper. And the numbers that you see there will show on the tension with respect to Planck using this method called Hellinger tension, which takes into account the asymmetry in the error bars, basically. So that's where we were in 2021, and this is where we ended now. So we have now less than 1 sigma different to Planck results. Okay, so we wanted to see what changes, how we got there. First of all, we can look at the Li et al. Analysis in 2023, which did a few changes to the analysis. One of them was to change the scale cut, so removing some of the smaller scales, and then it was to do a new shape measurement and also shape calibration. And this moved us a little bit higher. Also, fans of cosmology talks would remember that from the DES plus KiDS reanalysis, we found a similar shift once we removed some of the smaller scales. So these are consistent with that analysis. Okay, and then after that, we moved to changing the redshifts. So this one is when we change the redshift distribution estimation and the calibration method, but using the same data. And you can see that it shifts things a bit higher again. And then next, if we also add the extra redshift sample, that will help us with the calibration and redshift estimation, and also change the tomographic limits and fix them to what we have for legacy. This is another low shift. So you can see all the shifts are going towards where we're going to end up. And now if we go to the legacy data, again, we see another lower shift. So this is the same area as KiDS 1000, but using the final data release products, so new imaging, new image calibration, and sample selection, and new photozs. And then if we include our extra bin, so as you saw that we have bigger redshift range, that will decrease our error bars. And then another change that you see between these 2 points, two last points, is that we went from NLA, which was our fiducial intrinsic alignment analysis, to another model that we'll explain later. And that's basically main changes that the error bars shrink. And then finally, if we add the extra area that legacy provides, that does another shift. And then we end up at 0.73 sigma in capital sigma 8, and also similar in S8. So basically, if I want to summarize this, it's a combination of statistical shifts because of new data and systematic changes because of the way we analyze the data and calibrate things.
It's still a little bit suspicious that all of the systematic shifts were in one direction. Do you have thoughts as to why that did happen?
Yeah, so this is what we wondered about a lot when looking at this. We actually did many more analysis than what's shown here. This is kind of a summary of the things that we looked at. And there was nothing really suspicious that we could say it's something that's inconsistent in terms of statistics necessarily. It seems to be just a lucky or unlucky case, depending on what result you want to get.
So one thing I think it's important to say is that all these changes we did because we were looking for improvements in our method, not because we were trying to make the tension go away or push the result in one direction or the other. So we've, wherever we could, tried to be careful and be as blind to the outcome of these things as possible and really come up with objectively improved data analyses or larger calibration samples or better selections, etc.
Yeah, I think that's valuable and important to stress. I mean, I guess there's always this sort of subconscious thing that you're not in control of entirely. But yeah, at a conscious level, it wasn't that you saw the final thing and went 0.73 sigma. Whew. Okay, we're done.
Well, but that's also why we have the three blinds, right? One of the three blinds was fully consistent with Lee et al. And this is part of the reason why the outcome was somewhat of a surprise to much of the team, because we, like you at the beginning of this conversation, had the subconscious feeling of, well, all things considered, we've only increased the area by a small fraction. There's a good chance that we're going to recover previous work. And we did.
Well, yeah, let's get into the blind discussion now then. Surely you knew when you apply each systematic change which direction it's going in. So you know that before you made the changes, you were consistent with Lee et al. So therefore, if it shifts up by 2 sigma, you know that you've moved away by 2 sigma from Lee et al., right?
We didn't do any of this analysis that you can see on the slide in front of you until after unblinding. So the analysis that we did on KiDS Legacy was with a completely different Redshift calibration sample, with completely different shape measurements and imaging calibration, with the new tomography, with additional high Redshift data, etc., etc., etc. And all of that meant that there was really no direct possible comparison with data products we produced for Legacy and data products that we had previously produced for KiDS 1000. So even if we wanted to, there wasn't an obvious way that we could have looked at, for example, the Redshift distributions and said, oh, things have moved in this manner.
So basically, when we did the legacy analysis, we fixed the analysis method and then applied it to legacy, but didn't do, say, the KiDS 1000 equivalent analysis on legacy, then change it to the legacy analysis. So there wasn't 2 versions of legacy to compare with each other.
Yeah, I mean, maybe I have in mind that, you're changing systematic one by one, and even on your like newest data where you don't know how it relates to KiDS 1000, it would still be that if you change systematic A and things shift up, and then change systematic B and things shift up, that you're like, oh, okay, I know the story this is going to eventually tell.
No, 100%. And we didn't do that at all. We implemented all of these various changes that you can see here on principle and ran the KiDS Legacy analysis from end to end as one unit on the 3 blinds. And then only after unblinding went, oh, we should probably explain where that difference came from. And in fact, one of the things that we can discuss is the fact that our blinding system is sufficiently strict that it actually hampered the analysis of KiDS Legacy in a fairly substantial way, because we couldn't compare to previous work from KiDS 1000 in any sort of meaningful sense. And that's related to changes to the imaging that introduced a minority failure in parts of our imaging that took us almost a year to uncover, because we couldn't directly compare what we had done with KiDS 1000 to KiDS Legacy. That's the level of investment that we put into the blinding process. We chose to take that year of hard slog and work rather than sitting down and going, that's it, drop the blinding, match the two things together and find out what's causing this issue.
Yeah, so as Marika showed, a significant portion of the difference that we found with previous work from KiDS 1000 and what we've done with Legacy comes down to the way in which we estimate redshift distributions and the way in which we calibrate redshift distributions. That is how we determine the bias inherent to our redshift distributions. And in both of those regards, what we've done in Legacy really pushes us into a new regime of accuracy and precision. And one of the main ways that we've developed our redshift estimation and calibration is by vastly expanding the sample of spectroscopic redshifts that we have access to in order to do that calibration. And the way that we've done that is through the compilation in data release 5 of this thing which we're calling KiDS, which is essentially KiDS and Viking-like observations over these spectroscopic calibration fields that you can see. And that gives us a much larger sample of sources, both in terms of various redshift baselines, but also in terms of area on sky, which tamps down photometric noise and sample variance, in order to estimate redshift distributions in a more robust way. To give you a nice visual of how we've increased the sample of calibrating spectra going from DR4 to KiDS 1000 to DR5, these red spectra that you can see is the entirety of the DR4 spectroscopic calibration sample that was used to generate the redshift distribution estimates and bias estimates for KiDS 1000. In Legacy, we have access to more than 5 times the number of calibrating spectra, courtesy of the KiDS observations. And that really helps us to ensure that areas of the color magnitude redshift space are well sampled by the calibrating spectra that we're using. So this is increasing the number of calibrating spectra that we have access to. Another thing that we have changed is the way in which we actually estimate spectroscopic redshift distribution or redshift distribution estimates from spectroscopic redshifts. And the way in which we've developed that method is to move beyond what was the previous state of the art, which in KiDS 1000 we called gold class, which is essentially asking the question, in an n-dimensional space of color and magnitude and redshift, therefore, how many cells are occupied by calibrating spectra, and how many sources in our wide field shear sample have corresponding spectra that they can be used to generate a redshift distribution. And if a wide field shear source resides in a portion of the color and magnitude space that doesn't contain a calibrating spectrum, then it is removed from the cosmological analysis because we don't have a calibrating spectrum. We can't generate a redshift distribution estimate for that source. That process was called gold class. However, that process is predicated on a noisy machine learning classification to discretize this color magnitude space. And you can see from the orange cells in this self-organizing map, which is essentially a two-dimensional projection of an n-dimensional color magnitude space, that the orange cells are cells that don't have a spectrum in KiDS Legacy. And if you look on the left-hand side, you can see the same space colored by redshift. Now, there doesn't appear to be a great deal of correlation between the orange cells on the right, and the redshift axis on the left. And the reason for that is because the association is fairly noisy. But if we repeat this association a number of times, then instead of having a binary classification of 1 or 0, represented or not, we can instead create a continuum. And that continuum tamps down the noise from this noisy machine learning classification and gives us something that we call gold weight. And gold weight now better traces the actual redshift axis that you expect to have some influence over the representation of individual sources. That is, we expect higher redshift sources to have lower weight because we have fewer calibrating spectrum at very high redshift, for example. And what we can see now in the gold weight axis is that you do have some correlations between gold weight and redshift and position in the SOM. And that's good. That tells us that this is now a more meaningful weighting that we can apply to our wide field sample in order to estimate redshift distributions more robustly. This process is then tied with new, improved image simulations of the actual spectroscopic sample that we have to calibrate, and that gives us new bias estimates. And the new bias estimates that we can make from colors based on this self-organizing map method, we can then compare and contrast to our independent redshift distribution estimate method, which comes from cross-correlation redshift estimates or clustering redshifts. And for the first time in KiDS Legacy, the simulated clustering redshift estimates that we get and bias estimates on the redshift distributions from clustering Z and from the SOM are fully consistent with one another. So what I'm showing here is the bias estimated using our color-based method in these blue lines, and if you focus on the red points, is the bias estimated from the clustering redshifts. And these are now fully consistent with each other when analysed on the same simulated sample, in this case from the MICE2 simulation suite. If we do the exact same thing now comparing the fiducial KiDS Legacy bias estimates using our image simulations, which are called skills, and we compare those to the biases estimated on the data from KiDS Legacy, you see the same plot, but now actually for KiDS Legacy. And you can see that there is a slight difference now in terms of some of the tomographic bins, but overwhelmingly the CCs are still fully consistent or very consistent with the estimates of bias we make from our multi-band image simulations from skills for KiDS Legacy. So this tells us that we have two independent mechanisms for estimating redshift distributions that both tell us the same story about the biases that we have on our redshift distributions. And that validates or vindicates all of the effort that we've put in to generating new methods and new simulations that are more realistic and give us a better estimate of these underlying biases. And in fact, when you analyze cosmology using the biases estimated from the blue lines or the red points, you find exactly the same cosmological parameters essentially. So there is very little indication or no indication from KiDS Legacy that the redshift distribution estimates that we have any sort of systematic bias with regards to our two independent methods of estimating the redshift distributions.
Another thing we updated was the covariance modeling. And when we started in KiDS 1000, we basically had different covariance codes to model the error of our observables for the different statistics, for the different tracers. And it was not a mess, but it was a bit cumbersome. And what we did then is to take all these things together, all the methodology that was developed in KiDS over the span of the survey, and write from scratch a covariance framework, which can calculate the covariance matrix for large-scale structure observables, especially photometric large-scale structure observables, which is always notoriously difficult to do. And we did this in the one covariance code, which is, as you see, by kids and for kids and maybe adults. And this already has been published last year in October. It's on the archive and it's publicly available on GitHub. But for the KiDS Legacy analysis, we validated this code against mock simulations. And what you can see here is the correlation coefficient of one of the main statistics used in KiDS, Xi plus, Xi minus. And you see in the lower half the analytic covariance and in the upper half the mock. And just by looking at it, you see that the general structure is the same, but we also tested if we just analyze everything with the mock covariance, if that would lead to a meaningful shift in the cosmological parameters, and it does not.
I might just quickly interrupt to do something on a slightly meta level, but for everyone. For example, Robert did not define here what Xi plus, Xi minus is. I guess this is a conscious choice by you guys, and I'm willing to go with that conscious choice because this is KiDS Legacy. Like if you want to go all the way back to the beginning, this video would be 3 hours long. However, KiDS members have given talks on this channel in the past. And for example, Marika gave a talk where she will have defined these things. I guess it's a little bit out of date now, so I'm not suggesting go and watch that whole talk and assume that everything that she says then is what they're doing now. What she said then is what they were doing then. But if you want to see things like psi plus psi minus defined, you could kind of skim through that talk. Or I think Benjamin Giblin also gave a talk before Marika. So if you want to see like KiDS itself defined, like what is this telescope, what was it doing? But unfortunately, we don't have time to just dwell on every single piece of the analysis. It is KiDS legacy, not KiDS first thing. But yeah, sorry for that interruption.
Thank you. So another thing, we checked basically what is the influence of different modeling choices now on the covariance. So when we change modeling in the covariance, how does this change our cosmological constraints? So this is what is shown on the left. You see basically the impact on S8. The gray band is the fiducial analysis, which basically has all the bells and whistles. And the different blue lines are the 1 sigma error bars again with the map. And we always switch out one thing which is labeled on the right-hand side of this plot. So for example, we turn off the supersample covariance term and we see how big this impact is. Or we turn off the non-Gaussian term and we see how big this impact is on the resulting S8 constraints. And we do this for a bunch of different things. We also do not include, for example, intrinsic alignment in the covariance modeling. We still have it in the model itself, right? Just about the error budget. Or we have this thing here, which is called the new mix term, which is some addition we did in KiDS legacy, which models one term of the covariance matrix better and includes the survey geometry. Yeah, so let's jump to the plot on the right-hand side. So Angus just mentioned clustering redshifts, and we also used the one covariance code to estimate the covariance which is needed to fit basically the clustering redshift distribution. And what was done previously, we basically used a jackknife covariance directly on, for example, on the data or on mice2 in this case. And it was never completely clear how trustworthy this jackknife covariance actually is and if it represents what we would expect. So we basically did the same exercise and applied the one covariance matrix to this problem for the clustering redshifts, where you basically cross-correlate a spectroscopic sample with a photometric sample. So with the photometric source sample, we wish to calibrate. And this you see on the right side, again, the correlation coefficient with the MOC on top and the analytic covariance on the bottom for KiDS 1000 setting actually, but you see already that the general structure is very, very similar. You see these blobs, the off-diagonal structure, and this gave us, again, a lot of confidence in the clustering redshift and that we are doing a sensible thing there.
You see these kind of like, it almost looks like coffee stain blobs. Is there like some interesting physics behind that, or?
So each of these blocks, of these like sub-squares, is one tomographic bin, right? And the tomographic bin peaks somewhere. And this is where this blob goes, right? Because there it has a lot of cross-correlation with the spectroscopic reference sample, right? And that's why you also see it goes to higher redshifts in each tomographic bin the further you go down. So when you go to the 5th tomographic bin, this is always to higher redshifts, right? This is where this blob comes from. And this is also something we wanted to understand, because we saw this, and in the mock it really looks like a coffee stain, and we were wondering what is going on. And it is actually there, yeah.
So one of the other developments that we made in Legacy was we fully reanalyzed the imaging that we use for shape measurement, and we improved the astrometric calibration and the photometric calibration. And while astrometric calibration usually isn't the most exciting topic to dwell on in a cosmological context, in this case, it's particularly interesting for Legacy.
What is astrometric? I've actually never heard that term before.
Astrometric calibration is the accuracy with which your imaging is aligned with the actual distribution of stars in the universe. It's essentially how you align your images on the CCD with the sky and tie them together across the entire thing. So it's the accuracy of
putting your CCDs into the reference of the sky, the night sky. And in KiDS Legacy, we have improved the accuracy of our astrometry, so the accuracy of this alignment, to a level that is quite a bit better than what we had in KiDS 1000 and DR4. So these distributions that you can see here are the differences between every individual square degree tile measured in KiDS Legacy compared to the reference, which in this case is from Gaia. We've made the same plot for Legacy, which is these points in the northern hemisphere. So this is delta right ascension, delta declination, and this is in the southern patch of KiDS. And we can compare that to the same plot measured for DR4 as a demonstration of how the astrometric solution in KiDS has changed, going from DR4 to DR5. And in particular, the dispersion of this distribution has gone down a lot. And that's because we've improved the astrometric solution and reduced some of the intrinsic scatter between the solution that we have in KiDS and the true reference of Gaia. So this was a victory for KiDS Legacy. But that victory didn't come without its own sort of twist in the tail, as it were, because one of the things that happened over the course of the KiDS Legacy blinded analysis was we discovered that there was a failing null test in the form of a significant B mode measured in KiDS Legacy that wasn't present in KiDS 1000. And this took a lot of investigation to find the origin of this B mode, and we eventually located it to a problem with a small minority of the survey's astrometric solution. So essentially what had happened is the improved astrometric sample, calibration sample, triggered a new failure mode in a minority of the imaging that wasn't present in any previous KiDS analysis, that led to about 1% of the survey area being biased in the shape measurement of individual sources that manifests itself as a failing null test, as a statistically significant B mode. So there's two important things to note about this. The first of which is the fact that we measured a failing B mode is actually a vindication of the null test process, because this is a demonstration that we constructed a statistic that we expected to be null. It was not, and it was not for a good reason, because we had unearthed a new failure mode in the imaging that wasn't there previously. We then went about finding ways to remove the B mode signal, and we did that through masking of these areas. So we found a statistic that we could correlate to the areas that we thought were pathologically affected by poor astrometry, not poor astronomy, that were pathologically affected by poor astrometry. And then by masking these areas successively, either by not masking any of the data versus masking approximately 1% of the sources in the survey, we went from having a B mode that was significant at a p-value of 10 to the minus 8, so wildly significant, to a p-value of greater than 0.01, which is passing in terms of there being no significant measured B mode. And so we used this as a way of constructing a new mask that allowed us to remove the B modes from KiDS Legacy. But crucially, we didn't just do this in the frame of the B modes. We also did this in the frame of our cosmological parameter estimates. And what we found is that even though KiDS Legacy has this significant B mode, the actual implication that that has for our cosmological estimates is very, very minor. So we saw that if we do nothing, we have a B mode that is highly significant, but our cosmological parameter estimates change by less than 0.3 sigma. Nonetheless, we don't like B modes in our survey, so we, as a point of course, mask out the areas of the survey conservatively out to this threshold here, which is shown in green, and that is now the actual fiducial data set that goes into all of our cosmological analyses. This entire process, of course, was performed blinded,
And then we analysed the final data set with this new mask in all the different blinds before deciding whether or not to unblind.
Every time there's like a failure of an L test like that, the like hidden inner skeptic wants to think like it might be some sort of exotic new physics that you're now interpreting as some sort of failure of an L test. But you know, you have to draw the line somewhere on how crazy you're willing to be about stuff like that. So
at about the 6-month mark into trying to find where these B modes come from, I also had that thought.
Do you want to put your crazy hat on, and what was the least crazy idea you came up with for what new physics might have been generating B modes?
I started digging through the literature at about the 6-month mark, looking for possible explanations of new physics. However, it was fairly clear from previous KiDS analyses that there had always been a non-significant B mode in previous work from KiDS. And because we had changed so much, I thought perhaps we had unearthed new measurements of the statistically significant B mode because we've added in higher redshift data, or because we've added in more statistical power, or because we are probing parts of the color redshift space that we hadn't probed before. And so we stepped our way back from the very last part of the analysis, the likelihoods, all the way through every step of the process, trying to identify where these B modes came from. And as it turns out, the origin of the B mode is the very first step that you take in generating a cosmological sample for weak lensing, which is calibrating your imaging to the sky. And this is why it took a year.
This is going to be a really naive, stupid question. Why do we need Gaia? Why do we not know what the time of day is and where our telescope is on the Earth and where the Earth is facing, and therefore precisely where the galaxy is when the image was taken? Or what breaks down in that method of measuring RA and DEC?
You don't know exactly where the telescope is pointing.
Okay, so but why not? Like, can you not go like with a protractor to the telescope and just measure the angle?
But it's moving all the time, right, as it tracks the sky. So telescopes, certainly modern active telescopes, are extremely dynamical things. So they track a guide star very well, but the absolute orientation is less easy to pin down.
The engineering side of just having some thing inside the telescope that like a level or something that says how have I moved is actually the more noisy way compared to saying, okay, there's that star in that image and I know precisely where that star is. Is that basically the answer?
I guess that's right. I wouldn't say 100% sure, but I guess that's right. But the point is that because we take every exposure, or every field that we observe is a number of sub-exposures where you shift the telescope slightly to remove blemishes and all that sort of stuff and fill in gaps between the CCDs. When you calibrate them, you have to really align them very perfectly. And for that, you have to have reference objects all over the field of view to do that alignment properly. And so the better your reference catalog, the more precisely you can do this.
Yeah, so as we have mentioned before, one of the other improvements in our analysis is a greatly extended series of internal consistency tests. And so the idea behind these tests is to quantify whether or not different mutually exclusive subsets of our data prefer different cosmologies. So I will go into detail about these subsets in a minute, but first, before we conduct this analysis, we actually need to define some metrics that allow us to quantify the significance of what we see. And this is summarized here. So we adopt 3 tiers of consistency metrics that all test consistency in a slightly different way. So the first one is an evidence-based metric where we test whether or not a split cosmological model, where we duplicate our cosmological parameter space and model different subsets with an individual set of parameters, where we test if this model is preferred over our fiducial model. So if the split model was preferred, then this would be a sign of tension between the two subsets that we'd want to test. So that's the first metric. Then the second tier is a multi-dimensional parameter metric So here we focus also on the split cosmological model, and we compute the difference between our parameter duplicates. So this is illustrated in the middle plot there. So we calculate the difference, and we look at the posterior distribution of the difference between, let's say, S8 omega m in that plane. And if this is now shifted from 0, then this would also tell you, okay, different regions of the data prefer different S8, for example, or different omega m, whatever we want to test. So this is in parameter space. And then the third tier is in data space. So there we take up our posterior distribution and translate it back into data space via the posterior predictive distribution. And here we test whether or not the observed data vector is compatible with being drawn as a realization of the posterior predictive distribution. And if it is, then it tells you, okay, that everything is fine. So as I said, these are all, probe the consistency slightly differently, like a single summary statistic, parameter space, and data space. So we adopt all of these three metrics for all of our consistency tests with different subsets of the data. So now talking about these subsets of the data, there are several ways in which we can actually split our data. So if you look at this plot, this just shows you our cosmic shear measurements with our primary summary statistic, COSABIS. And so each panel here corresponds to a combination between tomographic bins. And so what we can do first is we can just try to quantify the consistency between different redshift bins. So for example, we can pick bin 4, as is indicated here, and quantify if the signal in bin 4 and all its cross correlations with the other bins is consistent with the remaining redshift bins. And of course, we can do this for all 6 bins that we have in KiDS Legacy. And now, related to this test is the second one, where we look at the data vector again, and we look at the autocorrelation versus the cross-correlation signal. So as you can see here on the diagonal, we can see all the measurements for the autocorrelation of each tomographic redshift bin. So we select these ones, and then we test if these are consistent with the cross-correlation signals on the off-diagonal. Finally, we can also look at the data vector by looking at different scales. So here in each panel, we select the same data points, which are sensitive to certain scales. And then we quantify if these data points are consistent with the remaining data points.
So can I just clarify something? The little n here corresponds to like a scale cut then?
So in this case, it refers to the COSABI mode. So the COSABIs, they comprise the correlation function with a sort of filter function, and each mode is sensitive differently to different scales. So the first COSABI mode is just more or less sensitive to an overall amplitude in our two-point correlation function. While the higher modes, they're sensitive to some variations in the two-point correlation function.
So going left to right here, the data point in each box, the data points are different COSABIs bins. Okay, and then each box is a different redshift bin. So
all these tests, these focus on the data vector, but another test that you can do is you can take your catalog and split the catalog itself in different subsets. So this is what we also do. And for kids, one obvious way to split the catalog is to divide it into the northern patch and the southern patch, and which means that we derive a cosmic shear measurement independently in the north and in the south, which means that we infer 2 data vectors, which are now illustrated here as the green and purple data points. And then we can conduct our cosmic shear analysis and test, okay, does the constraints from the north agree with the ones from the south. And they do at 1.09 sigma here, as you can see there. So everything in that test looks very good.
I guess one has to do this globally rather than locally, but the Z15 looks very alarming, but I guess...
So when looking at these data points, you always have to be a bit cautious because they're highly correlated. So it's not, you cannot really tell just by doing some, okay, I don't show the best fit contours here, but if you do some guy-by-eye, this can be very misleading. And the 1.5 is not statistically significant. If you just calculate the probability to exceed, for example, it's perfectly fine. Yeah, so the final test at the catalog level is split into red and blue galaxies, which are illustrated here in red and blue data points, of course. And also here we find that everything is very consistent. So overall, all these tests, all of them indicate that really the KiDS legacy dataset is very robust for all different splits and different consistency metrics. So there's nothing that you would say, oh, this is something to worry about. There's nothing that we see that points out that anything is wrong. So it wasn't always as consistent as we have seen in KiDS legacy. So if you go back to the previous KiDS 1000 analysis, we have also tested the Redshift bins. And you can see the posterior contours here in yellow for individual bins and their cross correlations versus the red ones with the remaining bins. And now if you look at bin 2 here, this seems to be significant. So we found a significance at around 3 sigma here. This was something that we've seen in the previous analysis, but it's also important to mention here that for the overall constraint on S8, this isn't relevant, as you can see in the with the fiducial black contour here. If you just look at the red contour in bin 2, this is basically equivalent to the fiducial one. This is because of the different constraining power in different redshift bins. So if you just remove bin 2, basically your overall S8 constraint doesn't change. So this is something that we've seen there, and but we concluded that it's, for this analysis it wasn't something to be super concerned about, but it's still noteworthy. Now if we look at the same test in KiDS legacy, we see that things look quite different. So overall, all of these contours, they look very consistent. Of course, you also get the 6th bin that we didn't have before, which also looks very consistent. So here the significance of these shifts is at around 1.3 sigma. So very much, it's very much improved with respect to what we've seen before in KiDS 1000. So this also lets us conclude that this data set here is a lot more robust than what we've seen before.
It looks like bin 2 stayed where it was and all the other bins came to joy, isn't it? Bin 2's been saying, I told you so all this time. Yeah.
So also one thing to note here, that you have to be a little bit careful when comparing bin 2 in KiDS 1000 versus bin 2 in KiDS legacy. That's because our tomographic bin limits have actually changed. We went from an equidistant binning to an equipopulated binning. So you cannot really compare these. And of course, there's a lot more improvement in all the Redshift calibration process. So you cannot really say, okay, bin 2, the issue, whatever it was, is resolved. It's like a different bin. But still, we find no single bin is, as in tension as we have seen in KiDS 1000. So everything here looks very, very convincing. So in addition to the internal consistency tests, we can also test the consistency of KiDS legacy with the external data sets. And so we have conducted a full consistency analysis using our metrics with these external data sets, such as the cosmic shear data from DES year 3, then VAO data from DESI year 1, and type 1a supernovae measurements from the Pantheon Plus compilation. So individually, all these data sets were found to be in very, very consistent with KiDS legacy for all individual tests. And so this allows us also to then conduct a joint analysis of KiDS with these external data sets.
The DES year 3 here, is that their analysis or your analysis with a different pipeline?
So the DES year 3 here is based on the previous DES plus KiDS analysis. So it's a DES data vector that removes the overlapping area with KiDS. So it's the exact same data vector that was used in that work. And what we did here, we basically just updated the KiDS part of this analysis with the new KiDS legacy data vector. Yeah, so combining KiDS and DES year 3 gives us the ping contour here, which you can see is in very good agreement also with Planck, right? And now if we add the other two data sets into the mix, so the DESI BIO data and the supernova data, these really put a strong constraint on the meta density, and this results here in the black contour. And this gives us the most precise measurement of S8 with our low redshift data to date.
And with the Pantheon Plus part of this black vector, does the story change if you use either of the other kind of, Union and DESI 5 supernovae that people find popular, or does it basically look exactly the same?
So we haven't actually used the other supernova data sets because we found them to be basically equivalent. So we didn't do this. Also, if you can also make this plot only combining KiDS plus DES plus DESI without Pantheon Plus. Also, it's not significantly different from what we see here. The constraints are very, very much compatible.
And do you now combine with Planck, or is that kind of not interesting? Like, nobody cares about the actual value of S8 and the actual value of omega M. It's just whether different probes are giving consistent values.
So of course, when we conducted this analysis, blinded, we couldn't really, decide, we want to combine with Planck, because we didn't know that our S8 constraints would be compatible with Planck. But also, when investigating a combination of these early universe and the late universe data sets, this is always done in the context of extended cosmologies, testing this. And that's actually our plan for an upcoming work, where we then do the combination of KiDS and Planck to put constraints on extended cosmological models. So this will be done in the future. But here we just quantified the consistency between KiDS and Planck.
Just on that last topic of extended cosmologies, do you know off the top of your head, because I guess DESI are now seeing quite strong evidence when combined with supernova and CMB for this evolving dark energy. You can parameterize it by W0 WA, and it seems to be parameterizing whatever they're seeing relatively well. It's just an empirical parameterization, but it's a thing to use. How much does this kind of blow up? Certainly in the omega matter direction, I imagine it does, if you consider it in a W0 WA model where dark energy evolves. The reason I'm kind of asking is that I actually asked these of the DESI people, and they weren't sure either. And they said to ask the weak lensing people. But the idea is just that in W0 WA, they do blow up omega matter quite a lot. So if it doesn't blow up your shear measurements, you would then, in a kind of indirect way, be a good constraint for them on the W0 WA model, because although the S8 isn't particularly, if you have evolving dark energy, it doesn't change your S8 measurement that much. If you don't blow up an omega matter when they do, you might then indirectly kind of constrain W0 WA, not on your own, but when added to their data, by keeping omega matter tightly constrained, if that makes sense.
One thing maybe to keep in mind is that, so with the current sensitivity and the scales we're probing, we are not very, as you see in this plot, right? Cosmic shear alone is not very sensitive to omega n, right? Because we are basically only probing the power spectrum on the right side of the peak, right? So we don't resolve that so well, and we only get omega m constraint or sensitivity in a bit via the expansion function, a tiny and via the Poisson equation, right? Because we measure the shear, but then that is of course degenerate with the amplitude of the power spectrum.
Yeah, you might be completely right. Yeah, I was looking at the black plot rather than the pink one, but the black one has the BAO in it. And so for me saying that the blue one will blow up when you include W0 WA and your one won't, it might blow up to be half the width of the pink one, in which case, yeah, it's blown up, but the pink one is already bigger. Okay, that might actually be the resolution to why this is not something that people are super excited about. Okay.
So KiDS is, of course, one of the stage 3 surveys. And so we're keenly waiting to see what the dark energy survey, the hypersupermagnetron survey will show us. The other 2 stage 3 surveys. But these are projects from the ground. They're huge amounts of data and frontier stuff from what you can do from the ground with current instrumentation. But really, the future is to go to the next giants of facilities of this field, which is in space Euclid and later Roman, and the China Space Station telescope, and on the ground Rubin. And so these will not only give us better quality data, but also much more data. So Euclid is going to be basically 10 times the area of KiDS of sky and 5 times the sharpness of the images. So it's a complete step change in the kind of quality of data, the kind of measurements you can make. And so this is why we were saying before that the control of systematic effects is going to enter a whole new regime where many of these things will have to be improved again and maybe reinvented. So this is by no means the end of the field. It's really just a step on the way to getting much more accurate measurements. Specifically on the tension, there's the interesting situation that we've now pretty much reached the point where the ground-based data are as precise as what the CMB can tell us. So the CMB is basically limited by how much universe we can see, all sky at the CMB, and so it's going to be very hard to get a much more accurate sigma 8 estimate from the CMB.
Okay, even though they can measure smaller scales?
Yeah, but the CMB runs out on small scales, right? It becomes, the signal gets damped. So I'm not saying we've reached the end, but I think it's getting close to being exhausted. And so really large-scale structure at lower redshifts, maybe eventually in NH1, but also certainly now in galaxies. And in weak lensing is now, I think, for a while going to be the way to improve the precision of this field.
Cool. Before we wrap up, do any one of you want to let us know if there's any work being done in cosmology at the moment that you find interesting but underappreciated by the community?
Yeah, so I think one thing which is, well, it's actually in general done a lot, is baryonic feedback, and it's mostly probed these days, for example, with the Zaryov-Silovich effects. But there are also different ways to probe the baryon distribution in the universe. And one thing which is very, let's say, promising, and also which will give a lot of new data in the next decade or so, are fast radio bursts, which probe the baryon distribution, or the electron distribution, free electron distribution in the universe, and they're very similar to gravitational lensing. And there will be a lot of more FRBs coming up in the future with surveys like CHIME or CHORD, which is the follow-up, SKA, of course, or the DSA 2000. And these will also be interesting to incorporate in cosmological analysis to constrain galaxy formation. And yeah, there's also a very nice talk here actually by Stefan Hackstotz on in cosmology talks, right? Some years ago, 2, 3.
Yeah, some years ago. Would that still be relevant for people to check out, or?
No, I think as a introduction, it's still very, very good.
Thanks everyone for watching. Like and subscribe if you want, and leave a comment if you have a thought or a question. If you want a video to watch next, why not check out that FRB talk by Stefan, or one of the many other nice talks about cosmic shear on the channel. Other than that, thanks everyone for the great talk and great analysis.
Thank you.
Thank you.
Thank you.
Pleasure.
Thanks very much, Sean. It's been a pleasure to be here, and looking forward to seeing more of the cosmology talks in the future.